Hello everyone. In this video, I'll be talking about this paper titled Model Based Offline RL. The authors are Rahul Kidambi, Arvind Rajeshwaran, Pranit Netrapalli, and Thorsten Joachims. Um, yeah, I have jotted down some notes beforehand so that the video is shorter than usual, and this paper is actually a bit longer, so hopefully the video is shorter, so uh, for convenience purpose. So yeah, enjoy this video. Yeah, so this paper actually has 82 references, so you can assume it has a considerably good theoretical survey. So yeah, right into the abstract. Offline RL, which we have already talked about in previous videos. The goal here is to learn the policy using the data set which is already available and not interacting with the environment or the simulator any further. So, yeah, here the abstract says prior work in offline RL has been confined mostly to model free approaches. Okay, but yeah, there are a couple of good model based RL approaches as well, like MOPO. Yeah, MOPO in the previous video. Uh, I can put the link of that video in this video's description box, so check it out if you need to. So yeah, um, this framework consists of two steps. Yeah, the first step is building a pessimistic model p hat from the dataset, and the second step is to learn a near optimal policy. So the promise is that the value of any policy pi in this true MDP is lower bounded by this pessimistic MDP value. So yeah, this is the promise, and yeah, overall our framework, our MOReL is amenable to detailed theoretical analysis. Okay, we'll go right into the details right now. So yeah, introduction. So here it says an RL agent, yeah, is the usual RL agent which interacts with the environment, is actually slow and sample efficient, yeah, learning. So yeah, since we are learning from scratch, and yeah, we don't see the data completely, just it's on the go version. So yeah, it would need too many adjustments for it to learn. So yeah, I think that is one of the reasons why it is slow and sample inefficient compared to what offline RL should promise. So yeah, so here they describe what are the advantages of offline RL. Yeah, we discussed in other videos as well. So there's no concern of safety in learning in the training phase, because we are not actually interacting with the real environment. And yeah, the problem where dynamic programming and optimization um, and exploration are decoupled in this offline setting, because we are using the data set instead of interacting with the environment. So yeah, mm, yeah, some applications, I mean, yeah, like recommendation system has a lot of data, like autonomous driving. Yeah, a lot of applications for this offline RL. So now yeah, RL can also serve as useful subroutines, with a view of solving online RL as a sequence. Yeah, this is I mean, you could think of it to be an equivalent of offline RL, off policy RL, where in after each episode you're collecting data set according to some epsilon greedy policy, which is the off policy here. And you could also use offline RL's policy to be used in like on policy RL as well. So yeah, that is why these two are combined and called as online RL. So yep. In the next paragraph here, a few challenges are mentioned, like the distribution shift as the distribution shift. So consider row SA to be the state action visitation distribution, which may differ between the optimal policy and the dataset policy. So that is why there is the control of this distribution shift parameter comes into a picture. So here in this next paragraph, let's see, off policy RL algorithm with an offline data set. So as I said earlier, here it further says regularizing the learned policy towards the data set. Okay, the previous work. This is like usage of important sampling. You could look at Bertseker's dynamic programming volume 2 book for this. But this is very close to imitation learning rather than offline RL, because here since we are actually trying to mimic the data logging policy, we assume that data logging policy is the optimal policy, whereas in the offline RL data set might not be generated by an optimal policy. So that is one of the things to note down. In contrast, model-based RL presents a alternate set of approaches for using. We are directly approximating the model, so there are several advantages in this model-based setting. So you could look at my video on MOPO, which mentions more advantages of using model-based RL. So here they say that MBRL to be highly sample efficient in online RL setting, often substantially outperforming model-free counterparts. Okay. The MOPO paper as well suggests that biosimulations that the model-free RL outperforms MBRL in few instances of the dataset. Some structure where the dataset is a mixed policies, like optimal and the suboptimal version. So so here they present their contributions. Quickly overviewing this, the first one, construction of this pessimistic MDP. So they use something like positional information. So here assume these green instances of the transition probability matrix to be known. They classify that it is known if and only if that p hat SA is close to PSA, and other regions are classified as unknown regions. So they are usually transition to low reward and absorbing states. This is where the pessimism comes into picture. So the yellow part. So So yeah, there is a typo here. Yeah, why model based of for offline RL? Let's see. Yeah, as their distribution shift was mentioned, overestimation bias. Yeah, like values at unknown S and A pairs can be overestimated. So we need to characterize these limitations properly to say offline RL actually works. So yeah, to perform regularization towards data logging policy. Yeah, this is what the MOPO paper actually does. So yeah, forced to directly regularize in policy space, which is the um, model free approaches. So here, let's say model free approaches consider the space of pi, and then model based RL approaches considers the state action visitation frequency or distribution. So this here what they say is uh, this part, right? The green highlighted part. So uh, so it's actually richer, potentially richer. So that is why I have returned this as a subset. So but yeah, I think I can add one more point here. I don't know exactly, but I have seen this result in Syed et al. The paper titled Apprenticeship Learning Using Linear Programming. You can see theorem 2 in that paper. They actually say that the state visitation distribution and the policy according to that state visitation distribution are there is a one-to-one mapping. So I don't know if this is exactly true, but yeah, let's go ahead with the actual results of the paper now. So here they just summarize what are the theoretical contributions. Yeah, MOReL's pessimistic MDP construction, approximately lower bounds. Yeah, as I said in the abstract, from the abstract. Yeah, we introduce a new notion called unknown. Yeah, this is the USAD part, the position in information part, and then what about the third one? Okay, our bound shows that if static data set spans full support of the optimal policy, then yeah, MOReL guarantees that it can achieve near optimal policies, and the gap goes to zero. Further, the bound also captures the graceful degradation when the dataset doesn't cover. Okay, yeah. So they have clear-cut bounds. So yeah, that is very nice. We also prove that the tightness of a bound, showing that suboptimality of any offline RL. Yeah, the lower bound to complement this result, I think. So yeah, but I have actually seen this result. So yeah, the parameters like the discounted the discount factor, gamma, and I think there are a few other parameters which actually take some restricted values. Gamma actually just takes between 0.95 and 1. So I don't know if this is very generalized, but yeah. Let's see. Experimental results. Yeah, USAD as an ensemble of randomly initialized dynamic models and plans in the MDP with familiar policy gradient methods like NPG. So I mean, as we saw in MOPO, it's actually not a pure offline RL problem. So it's a mixture of like you. Yeah, I mean, I can explain this as we go along in the experiment section. So wait for it. Yeah, the algorithm obtains SOTA results in 12 tasks. So yeah, nice summary. So now going into the more details, the theoretical survey related work here. So offline RL problem, at least in the work. In the setting, high rewarding policy. So important sampling. Yeah, as I said, important sampling, it might be suitable for imitation learning that rather than this. So let us see what important sampling. Yeah, okay. So important sampling based off policy gradient methods are being cited here. So yeah, I mean, summary of important sampling, I can do that here. So like so let's say we have the data policy and any policy, and then any policy pi. So we need an estimation of like a policy gradient empirical like a policy gradient value for this pi. Yeah, we can use this important sampling to estimate the average, this average. So yeah, we could write this expectation in terms of the distribution corresponding to policy pi, and we can I mean, use the empirical estimate here like this, or instead by using important sampling, like first divide and multiply by p pi naught, which is the distribution corresponding to the data, and then this can be approximated by the expectation. Sorry to squeeze this in. So this is just the expectation according to pi naught of f of x times some weight. So this is the weight which comes into picture in the important sampling terminology. So yeah, some more details are provided, like I mean, we need some niceness property for the for this expectation to exist and so on. So yeah, shorter version of this explanation would be from this picture. So we have this blue distribution and this red distribution, and so we don't have the red distribution at hand. So we want the value for I mean the an estimate for the mean of that red distribution. So we can use the blue distributions estimate in this way by using the important sampling version. So yeah, that is a shorter version of that explanation. So here moreover, the results require strong assumptions and on data collecting policy. Yeah, by the optimal policy. Yeah, that is what I was actually saying. This method actually suits for imitation learning. So yeah, let's go further. Dynamic programming. Our recent empirical studies confirm that direct instruction leads to poor. Many papers actually show that. So yeah, finally a recent work. Okay, there is a recent work focuses on obtaining probably convergent methods for minimizing one step. Okay, duality theory. Okay, this is like yeah, min-max approach, I guess, like a robust setting. So yeah, model-based RL interplay between model-based methods and offline RL has been sparsely explored. Okay, yeah, maybe when this paper got published, was put into archive where they didn't realize about MOPO, I guess. So yeah, true. And subsequently planning and yeah, safeguards, yeah, which comes from this USAD part, which actually forces pessimism in the model. hmm So in contrast, we present a novel algorithmic framework. So yeah, let's go into more details. Okay, these are some advances. Okay, maybe some future and past work mixed up. So like how these works currently rely on, like yeah, this work actually borrows ideas from E3 and RMax. Let's see. Works critically rely on tabular nature. Yeah, even in this paper, like they assume finite state and action space, so yeah, could consider it as the tabular case. But yeah, finally the practical implementation will be focused on some kind of function approximation. But yeah, the results, the theoretical results are not given for the function approximation, but it's given for the tabular case. So yeah, that is one thing to know, keep in mind. So yeah, that is what I've written. Function approximation, the next step. Yeah, but the motivation for moving to function approximators without any theoretical proofs is that usually the neural networks, general prior works from many papers actually do the practical implementation. So yeah, that is one of the reasons. Yeah, in particular, model learning and policy optimization subroutines are extended from the ML framework. Okay, so let's get into the problem formulation. This is the usual formulation in any RL paper these days. So MTPM consists of is a tuple represented by state, action, the reward R, and transition probability matrix P, kernel, and initial state distribution rho naught and gamma discount factor. So pi is the policy, generic. So I've just written the the probability simplex version of it, because they actually use this version here. So yeah, this can be edited into the draft. So let's see. Yeah, basically we want to maximize this v pi, which is the discounted value function. Yeah, so let's see. So action is taken according to pi. This one, performance of the policy, and some star distribution. Same. We are interested in maximizing this thing over pi. Toward clutter, yeah, the subscript is removed here, and the optimal policy is pi star, which is the argmax. Yeah, so offline RL setting now. So yeah, we denote data logging policy as pi b. Although we do not require it in our formulation. yeah, so one doesn't need to know what this pi b is. So yeah, no need to know pi b. Okay, so here the goal of offline RL is to put pi out with a minimal suboptimality, and the difference between the optimal policy and pi out. Yeah, in general, it is not possible to find optimal policy. So we inevitable that there is a gap. So yeah, I mean, what they show for this result is complementing this part, proposition 4. Oh, sorry. Take it back. It's the next one. So yeah, the result which is complementing this is the corollary 3 here. Yeah. So it says the value from the pi out is actually lower bounded by this optimal value minus the gap which they actually characterize, give bounds. So yeah, we can only hope to reduce this gap in the imperfect data set regime. So yeah, when the data set is perfect, they also show that the gap is 0. So yeah, 0 when data set is perfect in the sense it covers the whatever optimal policy is covering, I mean the state and action visitations. So yeah, let's go further. Here the blue, the highlighted part, it says any offline RL policy can be upper bounded by this optimal value, but up to the gap of 1 over minus gamma squared. So yeah, I think this is the usual constants which one would get in the off policy regimes. I think with in addition, if we include functional approximation, then we would get one more 1 minus 1 over 1 minus gamma term. So yeah, so yeah, the optimality of this term would be just dependent on the what tool you are using, so for proving these stuffs. So yeah, let's go further. MBRL, specifically we construct M hat, which is from the P hat and rho naught hat. So M hat is the pessimistic MDP. So data collected by interactions with environment are used to learn. So for simplicity, we assume reward is known. The reward unknown part is actually closed. I mean, it is very similar to how you characterize, I mean how you control the transition probability matrix. So yeah, there's a typo here, MOReL. So yeah, if the authors view this video, then they can fix these things. Yeah, let's see. Again, J pi of this pessimistic MDP to denote the performance of correct. Okay, this closely tracks. Okay, that is the hope. Some policies may visit the imperfect dataset part. So yeah, I just wanted to say something in from this paragraph. So we have from pi b the dataset policy, we have the dataset D, and then from this dataset we are building the pessimistic MDP, and the the usual MTP theory concentrates on just history dependent policies. So now this pi b can actually come from this larger space, which consists of non-Markovian policies as well. So, but still, uh, this paper MOReL actually guarantees optimality with respect to pi star. So, disregarding pi b. So, yeah, which is the corollary 3 which I described here again. So, yeah, that is an interesting observation if you would like to think so. So, yeah. Now the algorithmic framework, let's see. So here the algorithm is presented. Given data set D, first build the pessimistic MDP. Oh, sorry, the pessimistic MDP is coming here. So P hat is constructed using the dataset, and then USAT is computed. Pessimistic MDP is calculated, and the optional step, which is the natural policy gradient, which we'll see later, is using. Oh, okay, sorry, this is not that step. Okay, this is to estimate pi b itself. Okay, to be used by a planner later, which is the natural policy gradient, which they will use later. But yeah, let's go into the details right now. Learning tree dynamics model. Yeah, so what it's saying is, to be safer, do not use the data on state and action pair which with insufficient data, which is what USAD is accomplishing. So yeah, this is where the overestimation bias is controlled. So yeah. Now what this USAD is, it's actually defined here. So alpha USAD is defined in this way, where you could say this the first line of the equation is data availability, which is this. So sufficiently close to the query in the dataset, and the features or representations used, certain features and such as knowledge of might be amenable to generalization guarantees. Okay. So yeah, so this actually, the point B somehow motivates towards exploring the unknown state and action space, but not by much. If the total variation distance between these two are large enough. So yeah, so I think alpha is the hyperparameter. It's like if you choose a really high alpha, then you would explore more unknown state and action pairs, and thus hoping I mean the policy which you get is better than what the dataset policy is, which is what the current paper MOReL is also actually trying to prove. I'll note this point later in the theorems. So let me go ahead. Pessimistic MDP, that is built here. So you are forcing if the USAD returns true, which is saying that the model is far away from the dataset model, then you actually send to the absorbing state called halt. So yeah, and correspondingly you would change the reward by putting a negative reward here. So yeah. So let's go further. Planning in pessimistic MDP. The final step is plan. Yeah, here many other methods can be used: MPC, dynamic value iteration, policy iteration, and so on. Yeah, but later what they use is NPG, which is natural policy gradient. So yeah, theoretical results. Let us go further. Heating time definition. Yeah, this is the usual heating time definition, T pi of SA. The first time where you take the action A when you are in status by pi. So this is over the subset S. So yeah, theorem 1. I guess this is the crux of the result, to say what they want to say in the later corollaries. So let me pass this through. Like yeah, these two bounds can be combined to say specifically for algorithm 1's policy, which is actually saying the value of the policy got by the algorithm is lower bounded by the value of optimal policy minus these terms. So where each of these terms signifies something. So here this one, it's the, so here actually they say what each term is. So yeah, the total variation distance between the, yeah, this is the true state action distribution versus the dataset distribution, dataset and true one diff. So this is the term which contributes to the gap, and others are, this is the exploration gap, like alpha. If it is low, then you won't be actually exploring more state and action pairs, and you would be pessimistic. And this last term, it's the heating time constant. So I think, how do I interpret that? Yeah, actually the further lemma, lemma 2 actually further bounds this part. So let's go ahead. Let's see if there is an interpretation for this here. So the key quantity determining, so yeah, they introduce a new definition for discounted state visitation distribution. So it's they'll use to upper bound this result. So yeah, the proof is very straightforward from this definition. So yeah. So coming to corollary 3, which is just using this equation star here. So star implies this part. So where the offline data set is perfect enough, so they set both alpha and TTV, the distance, as 0, because alpha is set to 0 because you don't need any further any further exploration. So yeah, so that is why only this term is appearing corollary 3. So what is this term? Can it be controlled, as what they talk about in the part which is coming up right now? So let's see. yeah, one can assume ud, the d of ud, sorry, 0, where this ud is the data, it's the state and action pairs which are not in the data set D. Is a set of state action do not occur in offline data set, guarantee finding. Yeah, this is what the previous results were doing. So now since U is a subset of UD, here this paper is actually using the model P hat that have not been seen in the dataset. So yeah, let's go further. Suboptimality bound on output policy pi out is extended to the setting where full support coverage assumption is violated. So yeah, this is 0 only when the dataset covers the true row. So yeah, so that is why this gap is significant enough somehow. Let's go further. So here significantly better bound than the depends only on this term. Yeah, the proposition 4, which was the lower bound in the gamma, is this part. Epsilon lies in here. The reward is in this range. The usual MDPM, rho naught, pi star, and the dataset policy. So better the data, better this value. So that is where this assumption is coming from, less than epsilon. So yeah, this is the lower bound for the true value function. So yeah, so actually for these parameters, the MDP the specific MDP which they construct is this. So there might exist some other MDPs as well. So yeah, here the all what this proposition says is there exists a MDP. So I think this proposition can be limited to the MDP represented in this figure 1. Yeah, it's a simple chain MDP which transitions from integer states. Yeah, let's go further. We see that for epsilon, this part, suboptimality of any offline matches the upper bound. Also implies any offline suffer at least the constant part in the first case. Yeah, the constant part, this part, yes. So going further into the practical implementation, yeah, I'll be short explaining this part because this is not so relevant to the theoretical contributions which is made here. So yeah, this is the part where functional approximation version comes into picture. So yeah, usual Gaussian parameters, Gaussian random variable is used. So yeah, so one would search for these parameters, mu's and sigmas, yeah, this is the least square method, so which actually gives what the weight vectors are. So yeah, the USAD part, the practical implementation is coming from E3 papers. So yeah, I haven't seen that paper, but like in this work we instead develop a practical heuristic for choosing. Okay. Yeah, from known to unknown regions by using the hard thresholding. So yeah, as I mentioned in my previous video on MOPO, MOPO actually does something called soft thresholding. This is hard thresholding. So yeah, this is hard thresholding. Yeah, so let's go ahead. Policy optimization. Yeah, this is the planning step which uses NPG. Yes, so thus the simulator is being accessed. So yeah, let's go ahead into the last few sections, which is the experiments. So this paper actually has extensive simulation, so yeah, that's good. The environments are these things: hopper, locomotions, and path searching environments. Let's see. We obtain a partially trained policy by TRPO. This is like suboptimal policies, which was defined in D4RL paper. So yeah, I can put the link in the description for that video as well. So yeah, feel free to watch that video. Data sets and exploration strategies. So yeah, noisy variant of behavioral policy refers to different noise processes. So they use noise processes epsilon greedy and Gaussian noise, yeah, to randomize the existing policies. So yeah, this is a good mixture. Some other details like the network parameters. Yeah, fight will ReLU. It's and our policy is represented by two hidden layer MLP 32. Okay, so 32 into 32 for policy space. Yeah, makes sense for the Mojoko environment. So but okay, let's see. We track the performance of policy learning algorithm by rollouts in the real environment, but these rollouts are used only for the purpose of tracking the learning progress, are never made available to the learning algorithm in any way. Yeah. Yeah, I have to correct what I've said earlier, I guess, right now. So yeah, this is just to get good policy. So yeah, I am mistaken here. So we are doing this step, the maximizing over pi of j pi's. So yeah, so we are not actually accessing a simulator there, so sorry for that. Yeah, let's see further. Yeah, these can be characterized as learning curves. So I mean, the usual on policy online RL problems, most papers present something called learning curve. So yeah, Now the three questions are being answered by I think 3 or 2 sections in the following. So let's go further. Yeah, how does the performance of practical variant of MOReL compare to the recent offline RL for different exploration? Yeah, impact of behavioral policies quality. How does the quality of data logging policy by extension the data set impact the performance of the policy outputted by MOReL? So as you collect more and more data set which covers most of the state action pairs, you would expect this constant to be 0. So yeah, one interesting experiment would be to mix these 2 points here, the first and the second one. So one would expect when the data is perfect and when comparing with offline RL, so you would expect MOReL and other SOTAs to perform very similarly. So yeah, this would be an interesting experiment. Now at last there is an ablation study removing some important steps, so that what happens when you remove those things. So pessimistic MDP construction help elevate distribution shift and enable efficient mode. Yeah, so yes, this was the DTV part, the total variation distance part there. So let's see here. So the compared algorithms are BCQ, Bear, and different variants of BRAC, MMDVP. Yep. So quality of logging policy. So yeah, so this table actually represents what the data set value is. The aggregated rewards are. So the pure partial data set is the one which is collected from the partially trained policy, and then pure random is the randomized version of the data set. So the epsilon gradient Gaussian noise policies. So yeah, okay, we could come back, remember these numbers at least. Hopper, let's say, and we want to, I'll remember 1000 and 3600. So let's see for and yeah, 3600, and it is more than that, so it's good. Oh, okay, it is. Yeah, so MOReL is performing better than all other SOTAs here for Ant or even for Hopper. Half cheetah. So half cheetah, few. So these two are performing better than MOReL. So and here as well. So I guess I have to read these papers now, and probably I'll make a video again. So yeah, why would Walker and half cheetah are something like locomotion environments? Hopper and even these are locomotion environments, but I think it has some objective to fulfill, and these two rather than half cheetah and walker. In a half cheetah and walker, you just need to walk. I mean, there is no end point in the reward structure, so yeah, maybe interesting finding where the the possibility of model based RL not working and working. So yeah, by the name, this might be model free algorithms. Let me just check. In contrast, the next best approach, right? KL. Where is the KL algorithm? Prior. Okay. Yeah, I can skip searching that. So let's see. Ablation study. So yeah, this is the usual study. Let's pass this over quickly. Pessimistic MDP construction appears okay. Harder for locomotion task. That is what we observed earlier in the previous section. So in these environments, policy okay, uncoordinated follower accelerated okay, the distribution fish issue. So our results suggest that slightly outperforms naive MBRL. Okay, so yeah, the comparison with naive MBRL is what we have. So policy improvement appears to be possible even without use of pessimism. Can have cheetah, whereas pessimism allows the learning to remain stable. Okay, pessimism tends to play a larger role when quality okay is poor. Untrained policies. Attempts to visit, rewarding the paths. Yeah. Yeah. So now let's see lot of number of planning iterations versus observe that naive approach is highly unstable, so it's stable. So if you can see in this blue curves here, it's quite stable, not in ant though, but the other environments. Let's see, what is this? MOReL utilizes pessimism to stabilize the learning process for the random case. Okay. So here how the value pessimistic MDP lower bounds. Yeah, here I think in Walker 2D somehow the blue curve is below the said lower bound. Not exactly sure what's going on, but yeah, let's move forward. Yeah, this is for the partial case overexploited by the planning algorithm. So yeah, here as well model score, the green curve is kind of performing better for these environments, and here it is kind of stable and reaching at the end, reaching the optimal value at the end. So yeah, okay, these curves are for naive MBRL curves. So yeah, coming into the last section. So not drift into unknown states that cannot be predicted. Theoretically we obtain suboptimal bounds prior work. Okay, experimentally we evaluate. Okay, modular structure. An interesting direction for future work is to explore benefits of use more sophisticated approaches such as multi-step prediction for model RL. So future work, prediction with abstention, so on. Okay. Model based is better than. So yeah. More broadly, fundamental question in offline RL is to understand limits of achievable performance on the per problem basis. All current works, including this paper, perform policy evaluation using new trajectories from the true MDP and use these evaluations to decide when to stop training. It has ended using the trajectories. Where did I miss that? It's the planning problem, so yeah, I got to restate that NPG is being used. Okay, so yeah, so it is indeed offline plus online setting. So yeah, so yeah, this is what the learning part was. So yeah, so yeah, now the acknowledgements. So yeah, these are the 82 references. Yeah, quite an extensive survey. So yeah, I think this is the end of this video. Hopefully you liked it. Yeah, if I made any mistakes or something like that, feel free to comment and correct my. So have a great day, everyone.